Pleasure to welcome Jingyin Huang from McGill University, and he's going to talk about commensurability of groups, quasi-isometric RAAGs.
Okay, thank you, the organizer, for invitation, and it's a pleasure to speak over here. So this is joint work with Bruce Kleiner. Okay, so let me just start by remind you what is a RAAG. Perhaps most of you already know. So all the graph in this talk will be finite simplicial graph, and we pick a finite simplicial graph that will be the vertex set of gamma. Then this gives rise to a group presentation where the generating set are in one-to-one correspondence with the vertices, and all the relators are commutators to generate the commutes if only if the corresponding vertices are adjacent in the graph. So this is called the right-angle Artin group, or the RAAG, with defining graph gamma. And we will use this notation G of gamma to denote this right-angle Artin group. So for example, if gamma is discrete, then G of gamma is free group because there's no relation. If gamma is complete, then we have a free abelian group. So in general, we can think RAAG is like an interpolation between free groups and free abelian groups. And the isomorphism problem of the RAAG has a very neat solution. So two RAAG, they're isomorphic if only the corresponding graph are isomorphic. So then today our focus is going to be on the quasi-symmetric classification. So this is the question we want to answer today. So we'll pick any group, let's say any finite group, quasi-symmetric to our RAAG G of gamma. So we ask whether we can categorize H algebraically. In particular, we're interested in this question. So can we say H is commensurable to G of gamma given H is quasi-symmetric to G of gamma? So this is the main question I'm going to focus today. So let me first start by remind you some previous works on this direction. So perhaps the most famous ones, this is also one of the most earliest rigidity result is like the free group of, so it's known that any group quasi-symmetric, the free group is commensurable to the free group. And then the next is if we have a free abelian group, then we'll also know a group which is quasi-symmetric to the free abelian group is commensurable to the free abelian group. So this follows from Gromov's polynomial growth theorem. And another case is, so you can take direct sum of free group and the free abelian group. Then it's also known that any group quasi-symmetric with this group is commensurable to such group. Another case is instead of taking direct sum, you can take a free product. So suppose we have a free product of free groups and free abelian groups, then it's already also known that another group quasi-symmetric to this group is commensurable to this group. So you see, like there's a lot of cases where quasi-symmetry implies commensurability. However, in general, the situation is not that optimistic. So I think the most famous counterexample would be the irreducible lattices acting on product of trees. So that gives you a group which is a quasi-symmetric to a product of two non-abelian free groups, but not commensurable to this Fm times Fl. So those counterexamples, they have like they have like some classical construction from number theory. There's also more recent example by Weiss and Berger-Moses. They have more exhaustive behavior, like they can be non-residually finite or even simple. So this group could be terrible. So another example would be this is called tree group studied by Burstock and Newman. So that's the class of RAAGs where your defining graph is a tree of diameter bigger than 3. So in this case, they're fundamental group of three-dimensional graph manifold. And so then you can find group quasi-symmetric with this group, but not commensurable by, you can take a non-flip graph manifold, then cannot be commensurable to a flip graph manifold. Also, you can even find another RAAG which is quasi-symmetric to this class of RAAG, but not commensurable to this class of RAAG. Okay, so these are the kind of all the previous works in this direction I know. So basically, so our goal today is we want to find a suitable condition on our defining graph gamma, such that we can always deduce commensurability from quasi-symmetry, and this literature will serve as a guide for us to put the suitable condition we want. So now let me state the result I want to tell you today. So the first is the following. So first is like a quasi-isometric classification within the class of right-angled Artin group. So we have this assumption that we pick a right-angled Artin group such that automorphism group is finite. So recall the automorphism group is the automorphism group modeled by the inner automorphism group. Then, okay, if H is another RAAG, then H is quasi-symmetric to G of gamma, if only if H is commensurable to G of gamma. So this is the so notice that here we require H is also RAAG. So this is the kind of a quasi-symmetric classification within the class of RAAGs. So let me mention something about this assumption auto is finite. So this actually was motivated by some previous QI rigidity result. If you think about higher rank lattices and the mapping class groups, so they have finite out, and this kind of vaguely motivated in that way. So also this finite out is some condition where which you can directly read from the graph. So there's a set of combinatorial conditions where you can check your graph is finite out or not. So so actually if you still remember, there's a one-to-one correspondence between RAAGs and the finite symmetrical graph. So it makes sense to talk about random RAAG by consider the Erdős-Renyi model of a random graph. Then there are people study like how large is this RAAG of finite out. It turns out that there's a work of Charlie, Fabo, and they show as long as the range, your parameter is in the correct range, then almost all RAAG has finite out. So that means this is a non-trivial class of RAAGs. Okay, so this is the first result. So and now the second result is basically we still want to relax this condition that H is also a RAAG. So we want to consider a case where H could be any finite generated group. This turns out to be much harder, and we need more conditions. Still, first we want this out finite condition there, but it turns out that if you only put this condition, there's going to be counterexamples. So now we're going to put another condition where gamma does not contain induced four cycle. So this basically means the group does not contain this 3 times 3. So this so it turns out that gamma does not contain induced four cycle is equivalent to your group G of gamma does not contain quasi-symmetrically embedded 3 times 3. So this was motivated by this irreducible 3 times 3 lattice example in the previous slides. So we want to rule out this situation. So okay. So the third condition is a little more technical. So I will tell you why I need this later on. But let me just first define it. So I want gamma to be star rigid. So that means if an automorphism of your graph fixes the star of a vertex pointwise, then alpha is identity. So I think the most simple example would be you can take gamma to be a polygon, and then you know if your automorphism fixes the star of a polygon, then it fixes the whole polygon. So also any graph which has trivial symmetry also satisfies this condition. So these are the 3 conditions I want, and in particular there exists a graph which satisfies all these 3 conditions, like all the polygons who has more than 5 sides or more than 4 sides will satisfy this condition. There's also higher dimensional, like you can take the one skeleton of a dodecahedron or some more complicated graph. So it turns out under this 3 assumption, the any finite generated group quasi-symmetric to this G of gamma will be commensurable to G of gamma. So and it turns out that the condition 2 is sharp. So in the following sense, so suppose we have a gamma which contains an induced 4 cycle, then we can always find a finite generated group which is quasi-symmetric to our RAAG G of gamma, but not commensurable to G of gamma. So basically, this is the main result I want to tell you today. So in the rest of the talk, I'm going to sketch a proof of the second theorem, and if I have more time, perhaps I will say a few more words about the first one and the third one. Okay. So this is the plan. So before I sketch the proof, so I need to remind you there's like a nice geometrical model where a right-angle Artin group can X. So let me remind you quickly. So every right-angle Artin group has a very nice Eilenberg-MacLane space called Savati complex. So the construction is as follows. So we pick a complete subgraph delta of gamma. So since this is a complete subgraph, that means every two vertices are joined by edge. So this will give you a abelian subgroup of your RAAG. So let's denote as G of delta sitting inside G of gamma. So and we already know what is the Eilenberg-MacLane space for abelian subgroup. So basically, we're going to associate that standard torus whose fundamental group is G of delta. So basically, here we actually define a functor. So basically, for each complete subgraph, we're going to associate a standard torus. Okay, and then this is indeed a functor in the following sense. So if you have one complete subgraph sit inside another complete subgraph, there's a natural inclusion of one standard torus inside another standard torus. So now the Savati complex is constructed by we're going to glue all these torus T deltas, where delta ranging over all the complete subgraphs of gamma together and with respect to this functor. So and then the resulting space is called the Savati complex. It's basically a union of torus where each torus comes from a complete subgraph of your graph. So it turns out that this is actually not hard to check. The fundamental group of this Savati complex is exactly your right-angle Artin group, and this space is non-positively curved. So its universal cover is contractible. So this is indeed Eilenberg-MacLane space for the right-angle Artin group. Also, we need two terminology here. So this kind of abelian subgroup G of delta, where delta comes from a complete subgraph, is called standard abelian subgroup. And these torus T deltas, they are sitting inside this Savati complex. We call them standard torus. They're going to play an important role in our understanding of the geometry of right-angle Artin group. So now we have this nice Eilenberg-MacLane space. We can pass the universal cover. So we net X of gamma to denote the universal cover of the Savati complex. Then this is a K0 cube complex because and then we have this nice action of G of gamma on X of gamma geometrically. So geometrically means properly co-compact by isometry. So this is so we have this nice geometric model for RAAG, and then here is actually another alternative description of this space X of gamma. So it's basically the one skeleton of this X of gamma is exactly the Cayley graph of your RAAG, and then X of gamma is the cubical convolution of the Cayley graph in the following sense. So you start with the Cayley graph. Whenever you find a 4 cycle, then you fill in a square. Then whenever you find the 2 skeleton of a 3 cube, you fill in a 3 cube, and then this will terminate after finite step. So this you exactly get the universal cover of the Savati complex. So and we define the standard flats in S of gamma to be the lifts of standard torides inside the Savati complex. And then if you think about how G gamma is X on X of gamma by left translation, then the corsets should be left corsets of standard abelian subgroups is in one-to-one correspondence with the standard flats in X of gamma. So since downstairs the Savati complex is a union of torus, then if you look at the universal cover, X gamma would be union of standard flats. So the way we want to think about this space is basically we pick a bunch of Euclidean space and glue them in some complicated fashion determined by this gamma, and the pattern of how this Euclidean space are glued will be crucial to understand the quasi-isometric rigidity of RAAG. Okay, so now this is the geometric model we're going to need, and then so now let's look at we pick some group H quasi-isometric G of gamma, and then there's also another small trick I want to do. So we have this we specify a particular quasi-isometry from H to G of gamma, and then let Q minus 1 to be the Qi inverse. So basically an inverse up to bounded distance, but it may not be a set theoretical inverse. Then what we want to do is we want to start with this left action, rho prime of H on itself. So this is a very nice action. We want to conjugate this left action by our quasi-isometry. So notice that the thing you define, you can always define this thing, but the thing you define here may not be an action. The reason is that here, the Q inverse is only a quasi-symmetric inverse. It may not be a set theoretical inverse. So in particular, in the quasi-action O rho we define here, the composition law may not be holds. However, we know everything is true up to bounded distance. So the composition law should also holds up to bounded distance. This is what I mean by quasi-action. So a quasi-action is basically action by quasi-symmetry such that the composition law holds up to bounded distance. So this basically tells you if you want to study group quasi-symmetric, if you want to study H quasi-symmetric the group, it's sufficient to study the quasi-action of H on G of gamma. Okay, so now this is basically now we are done with our setting up. So now let me indicate the strategy of how we prove the main theorems. So we pick H is quasi-symmetric G of gamma, and our strategy is actually fairly standard. So first we construct a nice space X where this H acts geometrically, and then we're going to study this action to deduce the commensurability of H. And then let's look. Actually, today my main focus is going to be the second point, but for the completeness of the argument, I will go through very quickly for the first part. So I will tell you what is the metric space we need. So actually here we indeed need a new metric space because we already have a metric space where G of gamma acts geometrically. However, it's not true that H can always act geometrically on that metric space. So there are counterexamples where H quasi-symmetric G of gamma, but H cannot act geometrically on this universal couple of Savati complex. So we indeed need a new metric space. So okay, so now we look at step one. So it further boils down to two smaller steps. So we first study the regularity of a single quasi-symmetry from G gamma to itself. Then we're going to study the regularity of the quasi-action of H on G of gamma. And then once we understand the geometry of this quasi-action, then we're able to construct this metric space. Okay, so this is the basic strategy. And let me also, let's look at this step 1.1 more carefully. So we want to understand the single quasi-symmetry. This further boils down to two steps. So the first step is we want to show this quasi-symmetry preserve top-dimensional flats in X of gamma. So this is also, roughly speaking, why we pick the top-dimensional flats. Because this is X of gamma is basically cat0. It's like a non-positive curved space. So it's natural to expect that those maximal Euclidean regions are stable under quasi-symmetry. That's why and the top-dimensional flats is the most simple maximal Euclidean region, and then this is why we pick those, and we want to hopefully to show they're stable under quasi-symmetry. So this is the first step, and then once we know this, once we have done this step, then we know the quasi-symmetry. We map top-dimensional flats up to finite host of distance, and they will preserve the coarse intersection pattern of this top-dimensional flats. So then we're going to pass to the second step. So basically, we're going to define a combinatorial object, which let's say roughly called the space of flats. So this space of flats is intended to encode the combinatorial of the intersection pattern of these flats. And then by the first step, we know every quasi-symmetry will induce kind of an isomorphism of this space of flats. And then the second step is basically, well, now we have this isomorphism of the space of flats. We want to reconstruct a map from G gamma to the self to deduce some rigidity property of this RAAG. So this is actually this strategy also used in several previous cases. So let me remind you. So if let's say in the case of when X of gamma is a symmetrical space of non-compact type or a Euclidean building, then we also know the quasi-symmetry preserve top-dimensional flats. And then in that case, the space of flats is exactly the Tilts building at infinity. So and then a quasi-symmetry will induce automorphism of the Tilts building at infinity, and then there's a result of Tilts, which saying if your building is thick and you rank, let's say the rank of the building is bigger or equal than 3, then basically any automorphism of the boundary comes from automorphism inside. So this is what I mean by reconstruction of a graph, reconstruct a map. And another case where this scheme appears is in the case of mapping class group. So where we already know, in that case, we know the quasi-symmetry will preserve those Den twist flats, so the abelian group generated by Den twist. And then in this case, so that the space of flats is basically the curve complex, which capture the intersection pattern of the Den twist flats. And that's this theorem by Ivanov says any automorphism of the curve complex come from a mapping class, and this. And from that, you can deduce some rigidity property. And this is basically what we do here. We also define an analog space of flats. Just look at how the flats intersect in the space. And we also prove our analog of T's or Ivanov's theorem says we can basically reconstruct the map from given isomorphism between the space of flats. So let me give you more precise formulation of what kind of map we get over here. So we say a bijection from G gamma to itself is called flat preserving if it sends vertices in standard flats, biject to vertices in standard flats. Here we basically identify this graph G of gamma with the zero skeleton of the universal cover of Savati complex X of gamma, and then it makes sense to talk about standard flats. So flat preserving basically means it's preserve all the standard flats, and then this is basically the map we get after we're doing the reconstruction. So we suppose the automorphism is finite, and let's rule out the trivial case where the group is Z. Then we can always, it turns out that any quasi-symmetry is bounded distance from a unique flat preserving bijection. So this is basically, we have a canonical representative for any quasi-symmetry, and this is going to be a very nice map. It's preserve all the standard flats. But now we need to be a little bit careful. So in general, a flat preserving bijection is not house of close to our isometry, even if this bijection is equivalent and a co-bounded group action, it may not be house of close to our isometry. This is quite different from the symmetric space of non-compact type. Yeah, so we will talk about this later. I'll give you an example. So now we have this. So this is basically we understand a single isometry. So now we want to use this to understand the quasi-action. Okay. So now suppose we have actions by quasi-symmetries of X H on G of gamma, and then by this theorem we can replace each quasi-symmetry in the quasi-action by a flat preserving bijection. So up to bounded perturbation. And notice that in the definition of quasi-action, so we say the composition law holds up to bounded distance. However, by the uniqueness statement in this theorem, up to bounded distance, there's actually a unique flat preserving bijection. So that means we actually get an action, not a quasi-action over here by the uniqueness statement. So basically now we have a action of H on G of gamma by flat preserving bijections. So this is basically the combinatorial information we're going to use to construct our space. So let me go back to one of the points I emphasized before. So in general, the flat preserving map may not be isometry or may not be house of close to our isometry. So this suggests the RAAG is much more flexible than symmetrical space of non-compact type or mapping class groups. So you should not hope for those more stronger formulation of rigidity. And then the main reason is it may not respect the order on each standard geodetic line. So let me give you an example. So basically, we take our group to be a free group, and then our space is going to be, let's say, 3 of 4 valence. So what we do is basically this black line is going to be a periodic line. And there's a translations along this black line, and there's various levels along this black line. So basically what we do is we pick this yellow line, and we're going to translate the whole yellow level one unit up. And we pick this red level, and we're going to translate the whole red level 1 unit down, and we fix all the other vertices. So this is well defined because we only define the map on the level of vertices, and basically we flip two levels, and fix all other vertices. And then it's not hard to check this is flat preserving in our definition, but you see this is not bounded distance from isometry, and this can be happen in more general spaces. So okay, so now let me tell you how we resolve this issue and how we construct our new metric space such that we get isometric action. So this is actually a simplified picture of the previous example. It's basically we have this line. This is like a subspace of previous space. So basically we'll flip these two lines over here. So I don't know whether you can see the color clearly. So we'll flip these two lines which are transverse to this vertical line. And then what we want to do is we want to pass to the following situation. Let's say, so in our new space, the black line and the blue line, they don't intersect, but they're connected by this little red edge. Similarly, this yellow line and this blue line, they don't intersect, but they're connected by this little edge. And then, because we have this little edge, once you flip these two lines, it extends to isometry of the space. So this is kind of the basic idea of what we do here. So what we do is basically we're going to add these small edges everywhere equivalently, so to allow some flexibility of our space to such that it's compatible with the action. So this is basically we're going to replace each standard line. Recall that standard line is basically come from standard circle in the Savati complex. We're going to replace it by a branch line. So we add all these small things, and then we're going to replace each standard flats by a branch flats. So a branch flats is basically a product of this branch line. As I told you before, originally our space X of gamma is basically you take a bunch of standard flats and glue them together. So now we're going to glue these branch flats in the same pattern as how we glue these standard flats. And then we just replace each object but keep the gluing pattern, and then we get our new space. So this is our new space X looks like. So basically it turns out as long as we choose this branch line carefully, so we can get an isometric action of our rectangle Artin group on a new metric space X. So this is basically finish the first part. So now we have isometric action of H on some metric space, which is also going to be a cat zero cube complex. Okay. So now let me let me talk about the second step. So basically this is the main focus today. So we have already seen that H acting the space where H acts is quite similar to the original space to X of gamma. It's just like a branched version of X of gamma. So for simplicity, I will just assume H acts geometrically on the old space. Okay, so to avoid some technicalities, this is actually already interesting enough for our purpose. So, and also for simplicity, we're going to assume H is a torsion-free. So we don't need to deal with OB folds. So now we need K to be the quotient. So basically now we want to understand the combinatorial of this quotient. So now I can tell you why I need this star rigid condition. So the star rigid condition tells you where H we're going to have a finite in that subgroup which acts on X of gamma in a label preserving way. So let me explain this next. Let me explain the label preserving more carefully. So recall that the one skeleton of X of gamma is exactly the Cayley graph of your group G of gamma. So if you think about how you define the Cayley graph, so each edge in the Cayley graph is of this form, let's say GS. So that means each edge has a natural orientation, point from G to GS, and each edge is labeled by the corresponding generator S. So that means basically the one skeleton of X of gamma has a natural orientation and a labeling. And then here I'm saying H has a finite index subgroup which acts on this one skeleton in a label preserving way. However, it may not preserve the orientation. So it's actually not hard to say if if H, the action of H preserve both the labeling and the orientation, then we are done. We get the commensurability result. But here we don't have this orientation preserving. So this is actually a quite serious issue. So let me give you some example. As the most simple example is going to be we can take our space to be R2. So let's say this is a copy of R2, and then let's say we label the horizontal edges by A and vertical edges by B. Okay, so now you can already see if you have action on this grid, if it's preserve both the orientation and the labeling, then that has to be a translation, and of course that's commensurable to Z2. But there's also the most simple example of action which preserves labeling but not the orientation is the Klein-Bottle group. So you have like a slide, you have like a flip, let's say flip of this B direction. But in this particular case, if you have a Klein-Bottle group, you can have a index 2 subgroup such that you preserve both the orientation and the labeling. Unfortunately, this is in generally not true. So in general, what happened is there actually are counterexamples. So basically, there are counterexamples of group acting on product of two trees. Let's say this tree is labeled in the way we want, and there are counterexamples. We have this group acting on product of two trees. They are preserving the labels, but there's no way to find a finite index subgroup such that the subgroup also preserve the orientation. So this is actually so that means the orientation issue is like a very serious issue, and this is going to be what we're going to fight with for the rest of the talk. So let me tell you how to deal with the orientation issue. So now first let me make several observations. So first, this label preserving condition tells us the following. So this label preserving condition will tells us this our quotient complex K will admit a graph of space decomposition where the vertex space and the edge space is of the same form. It's like X of gamma prime modeled again by a label preserving group action. So where gamma prime is some proper subgraph of gamma. So this tells you basically you can decompose this K into like a simpler vertices and edge space which are of the same type. So this suggests that perhaps there's some way you can use induction. Okay, so this would be the first observation. And the second observation is basically we already know that the issue we're going to deal with is this orientation issue, but it's actually quite hard to deal with this directly. So we're going to make our observation. It turns out that this orientation issue is exactly equivalent to something what Hagnan and Weiss studied before. They called virtually specialist. It turns out that if H is commensurable to G of gamma, that's the same thing as H has a finite index subgroup which preserves orientation. So this is equivalent to K satisfy a combinatorial condition called virtually special. So let me remind you what is virtually special. So a non-positive cube complex is special if it admits a local isometric embedding into some Savati complex. And this is definition of special, and definition of virtually special means it has a finite index, finite sheet cover, which is special. So if this okay, so at this moment, so you don't really so you can just you can just think this virtually special is some kind of combinatorial condition we want for our Cat0, we want for our cube complex. I will tell you exactly what we will need from this condition later. Okay, so now let's put these two observations together. So basically we already know this orientation issue is equivalent to virtually specialist. So that means if you have a theorem which tells you if all the vertex group and the edge group are virtually special, and then the whole space is virtually special, then you are done, right? But basically what we need here is we can use induction, and we need a combination theorem for virtually special cube complex. Basically the statement we need is if we know all the vertex space and edge space are virtually special, then if you have a graph of cube complex, then this graph of cube complex is also virtually special. So this is exactly the statement we need over here. So okay, so now, so basically we have reduced to our combination theorem. So now let me remind you some previous result on combination theorems. So for simplicity, let's assume our graph of space is just edge, it has only one edges, and we have two vertices, vertex space and one edge space. So just for simplicity, we can consider this specific situation, and here y1 and y2, they are virtually special cube complex. That means they are cube complex which has a finite index finite index cover, which is special, and we assume all the attachment map are all no quasi-isometries. Okay, so this is the setting up, and we want to ask when is this Z is this graph of cube complex virtually special. So the first result in this direction is by Hagland and Weiss. So the assumption are, suppose all your fundamental groups are hyperbolic, the vertex group and edge group, they're hyperbolic, and we also assume the edge group is man-normal in the vertex group. So let me draw you a picture of what this man-normal means. So it basically means, so if we have an edge vertex space, and let's say then we pass the universal cover of the vertex space. Let's say y1 theta is the universal cover of this vertex space y1. Then in this universal cover, you will see a lot of copies of universal cover of the edge space. Okay, and this man-normality geometrically means the cross intersection between any two copies of this this edge space is bounded. So this is what it means. So the two edge space, they could intersect or they could cross intersect, but they have the cross intersection has to be bounded. So this what it means by geometrically the group is man-normal. And then this result by Hagland and Weiss says as long as you know hyperbolicity plus man-normality, then you know your space is virtually special. Okay. So and then later this man-normality was dropped. And we have a kind of more general theorem where you only need to assume hyperbolicity. So let's say G, let's say the whole group, we already know the whole group is hyperbolic, and we only assume C is quasi-convex in your vertex group. Then you can deduce virtually specialist. So actually this theorem is pretty hard. It's kind of one of the key ingredients in the proof of virtual Haken conjecture. So what Weiss do is basically, in this case, where you will have this scenario where if you have two edge space inside the vertex space, but they have like unbounded overlap. So the strategy is basically we want to collapse this overlap to reduce to the bounded situation. So, but this is actually extremely hard to do because when you collapse those things, you have to keep track of the combinatorial data of your Cat0 cube complex, of your cube complex. And it turns out the tool was this something called cubical small cancellation theorem, and this takes 200 pages to prove this theorem. So, okay, so now, so our situation is basically we want to use these two theorems. But perhaps you already seen that we cannot use it directly. The essential, the main point is like hyperbolicity is essential in these two theorems, and without hyperbolicity, they are actually are counterexamples. So we cannot just use this thing directly, and then we also have to take care of QI invariance because after all, we want to say something about a group quasi-isometric over RAAG. So actually the first issue is more serious. So however, there are some ideas and schemes in the proof of this two theorem where we can adapt to deal with our cases. So now, what I want to do next is I want to review the scheme of the proof of this man-normal combination theorem. Is this theorem? Oh, sorry. So it's this theorem here. So I want to review the scheme of how Hagland and Weiss prove this theorem. And it turns out what we're going to do is we're going to use the same scheme with some adaptation. Okay. So now here's the Hagland and Weiss strategy to prove combination theorems. So we have this graph of spaces, and we assume y1, y2 they're hyperbolic and virtually special, and we assume man-normality. Okay. And then so now the strategy, basically our goal is to construct a finite cover which is special. So the natural idea is basically we have this graph of space, we're going to cut it in half. Okay, and then by our assumption, each half, because y1 is virtually special, that means y1 has a finite index subgroup which is special. Okay, and similarly for y2, there's a finite cover of y2, which is also special. But notice that when you pass to covariance of pi1, y1, or y2, there's also induced covariance of the edge space sticking out, right? So this is indicated by these half tubes around the covariance. So they're kind of the induced covariance of this edge space. And then the key point is, after all, we want to construct the covering of the whole space. So the key point is we want to match up these half tubes. So for example, we want to match up all the half tubes around this y1 to all the half tubes around this y2, and then we can construct a covering of the whole space. Okay, so this is the basic idea. So however, this in general is actually very hard to do that. So for example, here's a scenario. Suppose we have like we have two kind of half tube here. One is already good. We know. Suppose we already know this green one is going to map to match up with someone over here. But it could happen that there's like a bad one, which does not match up with any of the half tubes over here. Then what do you want to do? So the natural strategy is you want to pass to a further finite covering of y1 such that this good tube remains unchanged, but you can modify the bad tube. Then you will be in a good situation. So okay, so this can be achieved in the following way. So we have the following fantasy. Suppose the following thing holds. So suppose we have a retraction map from this whole thing to this bad tube, such that the image of the green tube is mapped to something contractible over here. Let's suppose this can be done. Okay, for the moment this can be done, and then we're in a good situation. Why? Because now if we have this retraction, and suppose we want to modify this bad tube by pass to some finite cover. So let's say there's some finite cover over this red tube over here. Then this any finite cover over this red tube will induce a finite cover over this thing by this retraction. Okay. However, we already assume this green tube is going to map to something contractible. That means if you pass to finite cover over this bad tube and pass to the induced finite cover over this thing, then the green tube remains unchanged, and the bad tube has been modified. This is the thing we want. So basically, once you have this retraction, then we can modify the bad tube and keep the good tubes. So okay, there's two things we need. One is a retraction, and another thing is we need this control of the image of the retraction image. It turns out that the retraction is there's always a retraction. So this is what we really need for special cube complex. So this special cube complex will guarantee such a retraction exists. So actually, we only have a weaker version, but it suffices. So what happened is basically we want to have a let's look at this picture. So what we want is we want to have a retraction from this to our bad tube here. Okay. So in general, it's actually it could be possible that does not exist the retraction from this to this bad tube, but what we know is there always exists a finite covering. Let's say this is a finite covering of this, such that this finite covering retract to this bad tube. So basically, this is only true up to pass to finite sheet covering, but this is still good enough for our purpose. So this finite covering has a name. It's called canonical convolution, and this retraction also has a name called canonical retraction. Okay, so basically we have this retraction map. And another key point is the key observation of Hagdan and Weiss in their paper is if we assume hyperbolicity and the malnormality, then the image of this green tube are trivial. So basically, so here the malnormality is used to prove the image of this green tube. These good tubes are trivial and this retraction map. So this is actually the most technical part of their paper, because so what they do is basically we have some assumption on the universal cover. We know in the universal cover different edge space that have bounded overlap, and then we want to deduce from that assumption that in downstairs we have trivial retraction of the images. So this is actually, it's usually very hard from upstairs to go to downstairs. If you have some assumption on downstairs, you can just pull back. But this is kind of the other direction. It's actually pretty hard. Okay, so now this is basically the strategy of Hagdan and Weiss. So basically we want what we want here. We want retraction, and we want control of the image of the retraction. So now back to our case. So our situation, of course, the bad news is both hyperbolicity and the malnormality fails. Okay, but there's several good news. So first is we only need to deal with covers of Savati complex or cover of branched version of Savati complex. We don't need to deal with general special cube complex. We have more structure. We can use the more finite structure of right angle Artin group. And another thing is malnormality does not fail terribly. So we have this no induced 4-cycle condition. Geometrically, this implies the following. So again, we still have this. Say this is our universal cover of the vertex space, and we have edge space inside. So since malnormality fails, that means the edge space could have unbounded overlaps inside the universal cover of the vertex space. However, if we have this no 4-cycle condition that tells you this unbounded overlap that quasi-isometric to Euclidean spaces of various dimension. So that means the malnormality does not fail terribly. So they're true up to this flats over here. So we have all these flats over here. So now, so these are two good news, and it's enough for us to. Here is like a very rough sketch of how we prove the theorem. So we're going to use the same schema as Hagland and Weiss, and still we need a retraction from the vertex space to the edge space. However, the problem is in the case of Hagland and Weiss. So since they have malnormality, they can claim downstairs the retraction is trivial. In our case, upstairs the overlap is unbounded, so they are Euclidean spaces. So in general, there's no hope to say downstairs you have a trivial retraction image. So what we did is, since upstairs the Euclidean spaces, then downstairs the best we can hope is the image of these bad tubes are tori of various dimension. So basically, the general scheme is if upstairs the overlap is something, then the downstairs should be that overlap modeled out by some co-compact group action. So now this is the first step of what we did. So the strategy is basically we're going to collapse. So this is basically a very rough strategy of what we do. We want, because our space has a lot of flats, we want to collapse these flats such that we obtain a hyperbolic special cube complex. Then we can use some work of Hagland and Weiss and go back to the original space. So this collapse procedure is going to rely heavily on the combinatorial structure of the right angle Artin group. So this does not rely on small cancellation theory, because now in this case there's no way to do small cancellation theory. But since these flats are intersecting in a very complicated way, but since it's a RAAG, so we can use there's something related to right angle Artin, right angle building we can use to do this collapse procedure. So now this is the first step. We get a control of the retraction image. So it's slightly weaker than before. The image is not contractible, but still we know something. So they're tori. And the second is,
when you collapse the flats, are you just getting the associated right angle Coxeter group, which is then hyperbolic because of the no 4 cycles condition?
So when we collapse all the flats, so we have the right angle building.
Yeah, I'm just wondering whether that's the Davis complex of the associated right angle Coxeter group.
That's quite similar. So it's the same construct Mac Davis, but when you collapse, it generally is not locally finite.
That's the apartment in the building.
Yeah, that's the apartment in the building.
I see.
Yeah. So basically this is we're using the Davis construction, and then there's something, because after you collapse the group, the action of the group on your space is in generally is co-compact but not purple. So that's give us a lot of technicalities, because if you look at the right angle building modeled by the group, in generally it is a cube complex, but it may not be non-positively curved. So there's some technicalities to deal with this issue. So we want to kind of pass to kind of branched covers to deal with that. So let me don't talk about too much details. So this is the first step, and then the second step is we want to still, once we have control on the retraction image, we want to, from covariance, we want to find a way to put all these tubes together. This also there's also something new here. So basically, so in the case of Haaland Weiss, so their retraction images is trivial. So it's relatively easy for them to glue the tubes together. However, in our case, our retraction images are twice of various dimension. So that means so in order to glue them together, we want to keep track of this combinatorial of this tori, like how they're twisted and the length of the circle inside. So we have to keep track of this all the combinatorial data to make sure that we can glue things together. So then there's another thing come up over here. So previously we rely heavily on this canonical convolution and canonical retraction, but they does not preserve such combinatorial data. So basically here we need some kind of modified version of canonical convolution and canonical retraction, so we can make sure that this combinatorial data are preserved, and then we can glue things together. So this is basically two kind of difference from the Haaland-Weiss theorem. And then once we have this basically once we have these two ingredients, then we're done. So also another remark is we're already seen that if there's a full cycle, then you can always find a counterexample. So what fails here is in step one, even if there's there are four cycles, you can still formulate some more complicated version of step one. So in that case, it will not be 2i, it will be some overlap. It will be like the overlap divided by mod out by some kind of bounded co-bounded group action. But what happened in the second step is if there's no four cycles, then the retraction image may have free groups inside, and the amount of combinatorial data you need to keep track of finite cover of, let's say, free group is too large, and this second step will fail. So it turns out that we can always find counterexamples if there are induced four cycles. Okay, so this is basically the sketch of the proof. Let me 5 minutes left. So let me just leave some questions over here. So we have three assumptions in our theorem. So we have this finite out and no four cycle and star rigid. So my question is, can we drop the star rigid condition? So this would be something I would like very interested. So currently I don't know any counterexample if we drop the star rigid condition, and I have no idea how to do it. So let me make some remark about this star rigid condition. So this we already seen that we use this star rigid condition to deduce label preserving, and there's a similar condition in the study of lattice acting on right angle building, what they call type preserving. So and I think if some of you know how to do some of the theory in the right angle building without type preserving, then that perhaps would be a way for me to generalize this theorem without this label preserving or star rigid condition. So another thing is, so what we really need from this label preserving is basically we need a nice graph of group decomposition and some kind of and the equivalence of this commensurability and virtually specialist. So actually I can prove some weaker statement if I know there exists some graph of group decomposition, which are nice in some sense, but in general I don't even know what we can hope. Okay, so this is actually quite similar to the situation of this Yang-Eagle theorem. So basically Yang-Eagle proves hyperbolic cat-zero cube complex are virtually special. So basically Yang-Eagle theorem is more stronger than Daniel Weiss theorem, because Daniel Weiss was working under the assumption where you assume there exists a graph of group decomposition, and the Yang-Eagle theorem does not assume there exists a graph of group decomposition, and the Yang-Eagle has like a very nice neighboring argument to get around of this. So basically one thing perhaps we can do is kind of try to see whether Yang-Eagle's argument also work for us. So whether there's a way we can neighbor things in a clever way, so we can get rid of this neighbor preserving condition. And yeah, perhaps let me just stop over here, and thank you for your attention.
Are there more questions?
And if the graph has induced 4 cycles,
Yes.
then the theorem is wrong. You can construct counterexamples.
Yes.
Can you say just one sentence on this?
Okay, so basically, still we want to first start with like group. It turns out if it contains induced 4 cycle, then we have a 3 times 3 embedded in our space. So what we do is basically we first construct irreducible lattices acting on 3 times 3, and then extend it to the bigger space. So in general, it turns out that this classical example, which come from number theory, they are residually finite, so they cannot be extended. Also, this Weiss example and the Berger-Moses example, so they are not. So in order to there are situations in order to extend the lattice has to be label preserving. So in the sense I described over here, so what I really do is first I construct an irreducible label preserving lattice on 3 times 3, and then once I know it's label preserving, then I can extend it outside. Yeah.
More questions? Okay, then let's thank the speaker again.